Hello, GOTO. My name is Vagif Abilov, and I'm speaking to you from Oslo, Norway, where I was supposed to board the boat on Wednesday morning. Unfortunately, it didn't work out, so I'm addressing you virtually, but I have important content to share with you. My GitHub account is called Object, and my Twitter name is OOObject with triple O. So it might hint about my professional attachment to object-oriented development. Still, I'm giving a talk which is called Life After Business Objects. So stay with me for the next 40 minutes to hear about my journey, my discoveries, and about what I'm doing now. If you have a question during the presentation, you can use a GOTO mobile app to write a question, and I will be happy to answer them afterwards. And don't forget to rate the presentation in the end. One thing I want to make clear, that this talk is not about the best programming paradigm. Actually, the talk is about being pragmatic. Eric Sink, in one of his blog posts a few years ago, he used the expression pragmatist in pain. And I think it describes pretty well transition which many developers that abandon object-oriented world come through. They're pragmatic and they become dissatisfied with how things work for them, with how efficiently they can design their system using object-oriented paradigm. For the reference, this is our product. We work with live TV, live radio, podcasts, TV on demand, radio on demand, news clips. It's a complex domain. We will not be going into details of our domain. Actually, we will begin with a quite simple thing, with basics, modeling a point. What can be easier than to model a point? A couple of years ago, I saw a great presentation by Dmitry Ivanov from JetBrains. It's called Immutable Collections in .NET, and I asked him permission to use a couple of slides from his presentation. Actually, it's one of the first slides where he was showing how quickly, for the very simple class, developers start making mistakes. And this is a plus point, which a lot of developers probably would write something like this. This is C#, in Java it would be something similar. And if you examine this class, this implementation, you will find that the implementation has 5 lines, and 4 of them are wrong, they should be there, and 2 of them are missing. So point as it's written now, this implementation, it's not thread safe. You can't really use it in a multi-threading environment. And of course, if you want to compare points, you should also implement hash code and equals. So the correct implementation will look something like this. But think about simplicity of point and how quickly developers start making mistakes implementing such simple class. For the comparison, this is data structures as we write them in F#. It's a functional programming language, and there are several functional languages available on different platforms. It doesn't need to be F#, but in .NET it's pretty much like default functional programming language if you want to do functional stuff in .NET. So that's it. Type point, and you don't need to remember of all these tricks which you need to do in C#. And yeah, so this is how you define point P. You define point Q, which can actually inherit some of the, not inherit, but get some of the properties of P. And it's consequences not of design mistake, I wouldn't call it that, when C# developers write incorrectly this point class. It's like insufficient experience, because like they're trying to write a class like the way it looks natural to them, and then but they must have bigger experience to write the class correctly. And I think there are principal differences between initial sets of defaults in OOP and functional programming. Because in object-oriented programming, it empowers you. It empowers you through a variety of choices. Actually, you can do a lot. You can achieve a lot, but it's your responsibility. In functional programming, it's safe default choices. It prevents you from unconscious mistakes, and it's very important. So, like, first thought about how you write stuff using functional programming. Very often, it's a right decision. It's a natural choice. And another important thing to mention is path to concurrency, which is given to you by functional programming, which is very important for modern application development. There is a so-called Amdahl's law, which states concrete numbers, which basically tells you if that part of your code can be parallelized, then how much performance gain you can expect if you increase number of your cores, number of your CPUs. And I guess most developers are just unaware how quickly you reach the maximum of your performance gain if you don't have parallelization in your code. So if only 40% of your code can be parallelized, then if you multiply by 10 number of your processors, then you will only achieve performance gain of like additional 56%. So that's something to think about. But let's have a closer look at business object, because this is the title of our talk, and we're still on a point. And this is our original class implementation from the first slide. And actually it's missing visibility qualifier. So it should be something like this. You see all these public methods. And the question is that why some of the dangerous methods, like methods that change point, why are they public? Because I don't want them to be public. But that's my only option if I want to expose public API. I have scenario of different scenarios. In most of scenarios, I want point to be viewable and not editable, and I have just some special scenario where I want to edit points. And only in this scenario, I want my dangerous methods to be exposed. So what should I do? Inheritance? Well, I don't think I need to explain that this is bad choice to implement something like this. Alternative is to move methods that change the state to separate class, something like point manager. Well, that's an option, but essentially it means abandoning point as business object, because this is what they've been telling us. Like you can actually make the object exposing its method, and what we're doing now, we're removing methods from the object, so it's no longer a business object. With F#, we use models as business logic scopes. So you have we don't actually mix data and methods that functions that apply to this data. We try to separate them. We have a type point and we have a module where we put methods or functions that we want to apply. And if you want it to be visible to everyone, then we just call it the same name as a type, and then it's available for everyone. But if you want to, yes, you see this example of code that uses it. But if you want to separate it, we have a different module, which is called point update, and we put these dangerous methods there, and only those client code that use point update, that opens point update module, only that code can actually use this dangerous method. Welcome to business objects. Business objects are the cornerstone of object-oriented paradigm. It's a holy cow. It's a sacred cow. It's a harmony between data and data structures and methods, operations on those data, which are attached directly to data structure themselves. But the more I worked in large projects which used OOP, and that was a couple of decades, the more the relationship between data structures and operations on them looked like this, like the painting by famous Russian painter Ilya Repin. These poor people, these are data structures, these are data, fields, properties, and they have no personal interest in dragging this ship, the boat of business logic attached to them for some reasons. And I will try to explain why I think it's wrong, why I think it's fundamentally wrong. I will be using the same domain or similar scenarios which Scott Flashen described in his excellent book, Domain Modeling Made Functional. Scott showed functional way of implementing this business functionality. I will be doing the same in C#, and similar code of course can be written in C++, in Java. It's order processing. Everybody knows this domain. It's typical workflow. You have unvalidated order, then order gets validated, price attached to it, and it all completes with order being shipped, or if the order is cancelled, then it's cancelled with a reason attached to the cancellation details. So how do we implement it in C#? Okay, so this is one possible implementation. You have class order with some properties like total price, tracking URL, cancellation reason, and a few properties which describes its state, whether it was validated, shipped, cancelled. But so far it's just data. So where do we attach the operations on order? Of course, one option is to attach it directly to the order. Of course, immediately we get drawn into discussions whether the order can validate, ship, cancel itself, or actually it's a prerogative of an external class. And actually this is part of what actually turns me off object-oriented development. Like these decisions are very much opinionated. Like different developers, great developers, will come to the same domain, and they will split these methods. They will attach them differently to data structures. Another option is to have order and order manager, and probably more experienced developers will take this path. Like you have the data structure, and then you have order manager, which encapsulate business logic. That's a way to go. One of the viable options. I just want to emphasize that actually we're abandoning this classical object-oriented approach here, because we have pure data and we have pure business. So there's not much of OOP left in this implementation. And this is exactly what Joe Armstrong found wrong with object-oriented paradigm. And he described it as different types of animals. And it's fundamentally incorrect to lock them up in the same cage. And I fully agree with this statement. So this is one way to implement. Like if I came back to object-oriented programming now, I would probably implement in C# or Java order processing the basic types like this. Very small classes. A class for each processing phase, and data attached only to those types which make them relevant, like total price have nothing to do with unvalidated order, tracking URL for shipment have nothing to do with priced order, and so on. And of course, all operations I would encapsulate in dedicated classes, and not just one class, not just order manager, single order manager, but just separate class for each operation type. Let's have a look at domain modeling in functional languages in F#. Already, when I showed on previous slide how I would implement today order processing in C#, it was similar to how we're doing it in F#. So it's very small types, and of course types, it's so-called record types, which just data structures, no operations, which contain exactly the amount of information which is used in that order processing phase. As you can see, we have order details, and the unvalidated order have just these details. Then we advance to validated order, and it has details and validation time. Then we price the order, and then total price comes. We can ship the order, and then there is a tracking URL, and if the order is cancelled, then there is a cancellation string. It's just those data, those properties that are used on each processing phase. And all operations, they are implemented in a separate module, which encapsulate all transformations. And these transformations, they transform from previous to the next type. If we start with an unvalidated order, and there is a transformation which transforms it into validated order, and from validated we can use price order, and you see all these methods, they only work on compatible types. You can apply price order to unvalidated order because order must be validated first. So then we can use it as a building bricks to build a business processing workflow. So you see, this is actually easily readable by non-technical people, because this describes the whole business process. Okay, we start with the product, which is book in this example, and then there is a pipeline, processing pipeline. We send it through validation, okay, validate order, then it returns validated order type. Then we can send it to price order, and then we price it, and then we ship it. It's worth mentioning that this approach, these functional transformations, can be implemented as pure functions without side effects. Mark Seaman had a great talk which is called From Dependency Injection to Dependency Rejection, which shows technical details of how this can be implemented. And of course, such implementation makes it testable without using databases, calls to external services. Algebraic data types in functional languages, it's a characteristic that can't be overestimated. In functional languages, you have both product types and sum types. Product types are similar to classes, to structs in languages like C# and Java. So it's a Cartesian projection. Example from financial domain, expiry date of a credit card. You have year and month. It's a product type. And for payment card, card number and expiry date is also, it produces product type. But in addition to product type, in function languages and in F# in particular, there are so-called sum types, either or. Example is funding source. So funding source can be either payment card or bank account, and there is no way you can define in traditional object-oriented languages sum types in such manner. You will have to use abstract classes with subclasses or interfaces, and it quickly becomes quite heavy. Also, you can typically you use sum types in code that uses pattern matching. And in pattern matching, you can use compiler to help you find out if you forgot some case to match. For example, we have isSourceValid method here, and it matches funding source on payment card and bank account. And okay, bank account, let's say it's always valid, but for payment card, we check expiry date. And if we forget the case for bank account, then compiler will generate a warning. And of course, if we treat warnings as errors, and we usually do, then your compilation fails. And with interfaces, of course, you won't have a chance to have compile check on that you have gone through all possible cases of your sum type. I should also mention active patterns in F#, which is quite powerful feature. They give you a possibility to implement a matching, a pattern matching on steroids, match on infinite sets. So you define so-called active pattern, which for every number, it defines property of being even or odd. And you can match on those properties for any n, which is integer. So you can treat the numbers like they were like just finite number of elements, and you can pattern match on them, like in this example. Nulls. A lot was said about nulls, about danger of nulls already, and I shouldn't be repeating that. But I want to stress out a different aspect of handling missing data, because developers who transition from object-oriented languages like C# and Java to functional languages like F#, for example, they say that, okay, we have nulls, and you don't have in core F# nulls, you have just options, and you have to be very explicit about handling missing data, which makes it impossible just to forget that this is a null and that it can cause null reference exception. You have options, so they guard you, they protect you from having nulls. However, options, while not being as bad as nulls, they can also be nasty because they still represent missing data, and they can corrupt your business logic. This is a quote from Yaron Minsky: make a legal state unrepresentable. And what he is emphasizing is that our code will become much cleaner, much easier to maintain if we exclude combination of data that are really illegal, that not correspond to real world scenario. So there will be much less ifs, much less branches in our code. The code will be more tight. And the same goes to optional type. If we rework our scenarios to exclude optional data wherever possible, then such code will be much cleaner and easier to maintain. So where we cannot live without optional values, it's domain boundaries, because the world is imperfect. And then when we read data from databases, when we get data from external services, then we have to deal with them. But the problem is that we often allow them into our core data structure, and they corrupt our business logic. We have to be very critical about allowing this imperfect representation of world to become part of our core domain. So we have to go through our data structure and find out how can we get rid of optional data. And one way is that if we just split our scenarios, if you remember this order processing where we had unvalidated order and validated order, and then on validated order there is some additional field which may come, like validation time, where in unvalidated order there is no such field. So if you had common order type, then it would drag all this optional data from between different scenarios: unvalidated, validated, priced, shipped. While if I have smaller types which correspond to different smaller business process phases, then we are able to keep those data types without optional data. Sometimes we just have optional data because they may be needed somewhere like in the processing pipeline in the future, when we about to finalize now data processing. And we have to find a way also to restructure such data, to hide this optional data so that they're not seen in the steps where they're not used. And there's a great talk which I can recommend. The whole hour talk is just about how bad are optional data. It's called Maybe Not, by Rich Hickey, by creator of Closure. The talk was in 2018. So those are also quotes from Rich Hickey, where he attacked this maybe type, which is option in F#, and trying to show like how bad they are for data processing. And on the left side, it's a picture from Rich Hickey's slides. It's shipped, and there is no optional ship. There is no maybe ship. Because you have to be very explicit. These are your data. On the right side, it's a record with slots with some optional data, and you have some holes, and it's harder to write algorithms which have to deal with these holes. So I went through some differences between object-oriented and functional approach. But what if we didn't make a change? What if we still were using C#? What would be different today? Could we make our system in C#? Absolutely, of course we could. So how can we describe the gain? How can we describe the advantage of switching to functional programming? And if I try to explain it just in one slide, just in one sentence, I would just say that it shortened the cycle from specification to production. So this is a value which is observed by and appreciated by our stakeholders. So we became more efficient as developers. We're writing more compact code. Comparing to C#, the code metrics in F#, well, it's roughly 50%, which is code is more compact. And it's more tight code. And it codes that fails not as often as it used to. So yes, we just became more efficient as development team. And if you try to summarize impact of F# on feature development cycle, so what actually makes us more efficient? So some of the important factors would be on domain modeling is use of algebraic data types. So we are quite efficient now in expressing functional requirements. And it's easy to read and it's easy to maintain. And that's a very important factor. Probably it's worth to be listed as number one. When I was switching to F#, that one of the reasons was like immutability, for example. But today, I would say that domain modeling is probably the most important reason for my transformation as a developer. Then separation between data structures and operations and use of small immutable records. It's very efficient. So we in C#, in Java, typically types, classes, they are important. They are we store one class per file. So we have as many files as we have classes. Classes are sort of big in a way. It's a big thing in object-oriented world. In functional programming, types are cheap to declare and not as verbose as in object-oriented languages. So types can be just like a couple of lines, and this is your type, some discriminated union on some small record. And then we have plenty of these small immutable records. And of course, we no longer need to keep one type definition per file. We have small file with 20 definitions. It is really very efficient. Elimination of nulls, and of course, what I was also saying a few minutes ago, that we strive to eliminate options by defining more tight data structures. And we use models to limit scope of business logics. So we no longer have this public API defined on public methods attached to data, which is visible to everyone. We have small modules which contain just logic that needs to be exposed for the given scenario, and we open this module only in the code that uses this scenario. So those are probably most important factors of our efficiency after switching from object-oriented programming to functional programming. So this concludes my talk about life after business objects. My GitHub account is still object and probably will always be. But I believe I'm now a better developer than I was when I created GitHub account and chose the name for it. And I hope that I managed to explain the reasons for this transformation. And I hope that these were good reasons and good transformation.